Good afternoon and welcome to this Bose Colloquium talk. We are extremely happy to have with us Professor Satish Ogale, who is presently the director of the Research Institute for Sustainable Energy, that is RISE in TCG CREST. He also is a professor at the ISAR Pune, and he used to be a chief scientist at the NCL Pune and also a full professor at the ISAR Pune. So, Professor Wagle is one of the very rare scientists who has worked very close collaboration with the industry. And today's talk is something which is very relevant to the transfer of technology or how the technology for academics can be useful for industries. So, Professor Wagle has did his PhD from, I think, University of Pune and joined University of Pune and then moved to several places. He has over 530 research publications, over 39,000 citations, and 10 US patents. He is a recipient of several awards, which and also the fellow of the Indian Academy of Sciences and the National Academy of Sciences. With this, I request Professor Ogale to continue with this.
ये भी है ना इसका
That's better. No, because then you don't, even if you move, it will remain. That's better. That also makes you feel like a rock star.
Okay.
Hello. Oh, sorry, Jana, volume over there. Can you manage the volume?
Yeah.
Now it is better? He will manage that. Okay. First of all, thank you, Professor Tanushree, as well as Pradeep Paskule and all of you for this kind invitation to give this talk. It is such a pleasure to be here because this is one of the exceptional institutes doing research in basic sciences. Is there a problem? Is it okay?
Yeah. Absolutely.
We do something to make it stable. Okay, I think this one is moving. मुझे लगता है ये right side को करो. It's on the right side. Okay, so I have visited this institute in the past about 2010 or something. When Professor Arun Chaudhary, Arun Roy Chaudhary, friend of long time, was here as a director. And now we have a very accomplished Professor Tanushree Saha has become to be a director here. And I've seen the progress that is happening. I just had a visit to a couple of laboratories, and it was such a pleasure to see how many young people who are doing some outstanding work here. So it is an honor to be giving a lecture here, which is a colloquium, and Satyendranath Bose, SN Bose Institute, and one of the outstanding scientists who taught us how to write a many particle wave function in the right way, identity of particles, spin and statistics, all that started with him. The way of writing the wave function, all of us teach in quantum mechanics classes, it was all born here and in this Kolkata. So we are very proud of this legacy, and you see the Bose-Einstein statistics, Bose-Einstein condensation, there was recent observations and so on. So the whole thing brought to my mind when I got this invitation that we are going to an institute named in his honor, actually. So what I'm going to do today is the talk that I have is Powering the New World, the Pursuit of Sustainable and Affordable Solutions. The reason I have given this title is that many of us who are doing our day-to-day job in laboratory, doing some research which has a value of some kind over years. This is some problem.
I think if
You
you
want
put
to
Let me
little
try the other
down.
one. Let me try the other one.
Okay.
Yeah.
We are not feeling very comfortable.
Yeah. I don't even feel like a star, as you say, or a TV anchor. Anyway, I'm an old star now, so I think I should not expect too much from this. Okay, this is better, slightly better for me also. Okay, all right. So I gave this title, Powering the New World, the Pursuit of Sustainable and Affordable Solutions. The reason is that currently we are going through a storm of changes in the world, and each one of us is like a small element in this whole scenario. And it is very difficult for each one of us to make any sense of what is going on and what is coming on in the next 5, 10, 20 years' time. And it is very important at times for us to sit back and try to understand where we are going, and how, as young people sitting here, how they can position themselves into this rapidly changing world. Okay, so this perception of complexity, which goes around in simply deciphering the complex information that we have around, is itself extremely complex task. Okay, and trying to see the threads of opportunities. Okay, they are clouded in the challenges which exist there, and it is very difficult. Many students ask me, should I go for AI? Should I do data science? Should I do this? Should I do energy science? Or do I go physics? What about chemistry opportunities and so on? The confusion is so high, that it is very difficult for making choices. It is also true that science, the shape of science in terms of the way it is done in the country, is changing over time to an extent that there is an applied science which is rising now in the country. The reason why applied science is getting important is because government recognizes that until the fruits of science are translated to society, it is very difficult to justify the taxpayers' money going into fundamental science only. Fundamental science is extremely important, as all of us know, because if you consider Raman effect, if you consider Bose statistics, anything that goes on that, so many things have happened in quantum technologies are emerging. We have the whole material science which has grown over through all these discoveries. So it is extremely important to keep doing fundamental science. But now the question is, while we do fundamental science, is it possible to understand some threads of our science? And if there is an opportunity to see that it can be translated in the interest of society, why not do that? Okay, so this is the question that people are asking. And you will see a lot of funding now which comes from BST, MNRE, and number of MIT and so on. They always say, do you have an industry partner? Okay, we have something. So, and the most things that people do is they say, okay, industry is interested, and industry gives a letter. We are interested in this, but they don't give me money. I was talking to Pradeep the other day. Some industry just do, like, I'm interested in your research. Okay, but they don't give actual money. Okay, then even then they are getting grants. But then later people realize that this is just so-called in-kind support. Okay, and that doesn't work actually. And I will give some examples where industry put, their pockets where their mouth is, and there are certain industries regionally forward-looking who are now ready to put some money because a lot of problems are there, the complex situations are generating that it is not just a commission type of business that Indian community can do anymore. Okay, we have done business over last 10, 20, 30, 40 years after independence, which was mainly related to bania type things. You buy something from there, packaging something, we cannot call that as made in India. That is assembled in India or packaged in India. Okay, but that particular thing is not working anymore. And even the precursors and other things which are coming from other countries and so on, there are tariffs on that, and there are different duties, international relations, complexities, and so on. So all that is guiding the principles of how research is to be done, and research funding is to be acquired, and research funding will be given, and so on. I think so for young people who want to do academics, they have to keep a track of all this. Okay, so I will just breeze through some of the things, slide just especially in the interest of students. Okay, so if you see the whole world around us. It is changing so rapidly that we don't have a sense of it. Each one of us knows autonomous car, each one of us robotics, each one of us know wearable electronics, AI, machine learning, robotics, energy, and then we have so many things here which are extremely smart, smart hospitals, smart cities, smart highways, smart factory. We are the whole lot, I think. And the whole world is changing in such a way that how we can accommodate these changes into our lives and try to make a sense of it is very important. Okay, so in this particular scenario, we have to understand this concept that if you look at this goal, United Nations has made meeting the needs of the present without compromising the ability of future generation to meet their own needs. So how we can do responsible science so that we don't screw up something so badly that our children and grandchildren and everybody, will suffer heavily just because we were selfish to look at our own needs and we didn't bother to see what is going to happen after 100 years. This definition is very, very interesting that they have made. And this affordable and clean energy, point number 7. I just looked at other points. There are 17 points sustainable goals. SDG, these goals, sustainable development goals. Okay, out of these 17 points, point number 9, 11, 12, 13, 6, 8 depends on what we do with point number 7. Okay, so if you look all of them, industry, development, innovation, everything is related to that. Therefore, doing good with clean energy will be good for our people and our nations. Okay, so that is why it is very important that we talk about clean energy here, which has consequences for everything else. Okay, now if you look at what is happening, we are talking about net zero carbon. India has pledged in the Glasgow summit of 21 will do net zero by 2070. Okay. And now what is net zero? 50% of total energy requirement by 2030 has to come from renewables, like solar, wind, and everything. Actually, everything, even wind, is produced by sun. Okay, so sun is our main source of everything, all other forms of energy, water, thermo, everything. So that's why sun is the main thing, and solar energy is the main thing in all this. But then 50% of energy requirement, we may be around 10, 12, 13%, and we have 2030. We are already in 2024, 6 years. We will do that? We have a question. We have to reduce 1 billion tons of greenhouse gases by 2030 out of the projected 4.5 billion tons that we emit and so on. These numbers are staggering, and we have to see reducing carbon intensity, and we will have to produce 500 gigawatts of renewable energy by 2030. Okay, so this is all targets which have to be met if we really want to do something net zero and so on. But you see here, the other thing, we always talk about electric mobility, EV, right? We always talk about, I will take a scooter which is battery-based scooter or a motor which is electric motor and so on. So all of us say, okay, we do well with that and we are going to control emissions and everything. But remember here, when I looked at this slide, it is only here, getting around, trains, cars, buses, all of that, only 9% of the total carbon emissions are related to that. What about manufacturing sector? Okay, cement, steel, aluminum, etc., 28%. Plugging in electricity from coal, etc., 34%. Growing things, food, fertilizer, 18%. So out of this, something visible, electric transportation, mobility, is something we say we are doing good, but there is a lot of other work to be done if we want to really do something. All these other sectors will have to cut down on greenhouse gases to be able to do something reasonable for our country. Okay, now 40 billion tons of CO2 equivalent that we are adding in the atmosphere, and in line of that, we have to do net zero. There have been many scenarios that people have worked out. Okay, how much will the temperature rise at the end if we do something solar, something more solar and something more renewable, something even more renewable and net zero around 2050 or something. If you want to do what are the discipline scenarios of doing something good with the way we live and the way we use energy. Okay, all those things are important. People, different kinds of NGOs have worked out these scenarios in different ways, and they have given some solutions, possibly what we have to do. In spite of this, the temperature or the rise, median surface temperature is going to rise by 1.4 if you do the very best that we can do. Okay, so this warming, etc., realistic scenarios in light of that. But unfortunately, you see here, this is what Shivaram once talked to me, and I was stunned by this. Over 400 private jets were used for traveling to Egypt for environment conference. Okay, and a private jet, you know, emits 2 tons of CO2 per hour and more than 5 to 15 times carbon emissions per passenger. You know, this is our, people are trying to talk about doing good. You know, of course, they cannot go to on bicycle to Egypt, but they could have all assembled one single plane and got there. Okay, simple thing as a practice to do, but that didn't happen. Okay, now we have, in order to go to energy, we have 3 basic scenarios: energy harvesting, energy storage, and energy conservation, which relates to lighting, optoelectronic materials, and so on. It is very important that there has been a tremendous progress made in this sector, where we have solar cells, where hybrid perovskite solar cells here have made many headways, and we have crossed efficiencies of 30%, 31% in tandem solar cells using hybrid perovskites and so on. However, there are many catalysts developed in CO2 to value chemicals, N2 to ammonia. This is also equally important for fertilizer context. So catalysis development is something which is a major field. And there are so many different interesting materials people are working on. Storage, on the other hand, is absolutely a must for renewable energy sector, because renewable energy is temperamental, and temporally also not available when it is consistent with your needs, and therefore what you need to do is you need to have storage. Unfortunately, storage is extremely expensive. Okay, solar cell costs, silicon solar cells have gone down dramatically over years because of the perfection of technology. Okay, and a lithium battery is much more mature technology, costs are reasonable, but still far more in terms of the scale that you talk about. Also, you can understand, each one of us in our mobile, you have seen a mobile battery, which is like a prismatic cell of, let's say, about 4 centimeters by 5 centimeters or something, that small cell. Imagine now we have each one of our car by 2030 or 2035 electric. It has a battery pack of this size. Okay, then you consider a truck. Truck weight maybe a few thousand kilos, and the battery pack maybe itself a few hundred kgs, and so on. Okay, intercity buses, and so on. So much of lithium, where is it going to come from? The point is, there are only few mines in Argentina and somewhere where China has already bought those mines. Okay, and we have discovered something in Saurashtra, something in Jammu. We say we are very happy with that news. But the point is, we are very weak in purification technologies. Okay, I always tell, my father was a geologist and he was a mines manager at one time. And in Andhra Pradesh, iron ore mines. I used to go there as a child and see what they are doing. So they were mining iron ore, Fe2O3, Fe3O4, whatever is coming out, and then all that was getting filled in trucks. So I asked my father, so kahan jata hai? Where does it all go? He said that it goes to the port and then goes to Japan. And Japan purifies it, makes something, iron, steel, and we buy it at 100 times more price that steel. Since then, we have never learned. We don't even know how to have a pure silicon made in this country. Okay, and therefore we miss all buses of making solar cells, making chips, and so on. Now with new semiconductor mission, new solar mission, and so on, all these things are going to happen. But even if we discover lithium a lot, we'll have to see how to purify that to a battery level and then incorporate it into different compounds. So there are huge problems which have to be sorted out like this. Okay. And now, when we consider, when I said that research, traditional research, which is for advancing science, is very important. But equally, translational science, which is goal-oriented, is very important. And what we need to do is, we need to ask, therefore, material science is something which is acquiring a center place. All of us have our discipline. I am a physicist, somebody is a chemist. All of us are very good, and we are contributing something. But people will have to come together to think of a problem, and then whatever discipline is there, they have to put together to solve that problem. So it is not a question of, I am a physicist, tell me what I can do. Okay, it is, what is the problem? We have impure water. What do? Then physicists, chemists, whoever wants to come together, have to come together in an interdisciplinary mode to solve that problem. So it should be the problem-driven research rather than my capacity-driven research. Okay, I can do something, and that is, tell me what I can do. I cannot tell you anything. You decide to do something which solves some problem. Okay, and then in that you can do fundamental and applied science and all that. And in engineering is extremely important. It is not simply, see, it is very important to take laboratory science to market, and all the different steps have to be taken. So what we are doing in material science is putting together diversely functional materials of different interesting properties together with different property portfolios and creating novel effect in the interest of sustainability. This is what the material science goals are right now. Okay, now here nanotechnology has some very important role to play. As all of you know, many people jumped on the gun of on the boat of nanotechnology some 20 years back. Everything was converted into nano study properties. We acquired nanomission, several grants, and for 10, 15 years, it all went into research. But eventually the question was, where all this research is going? Okay, so where is the application? Only in the last 7 to 8 years, nanotechnology is coming of age and becoming mature to be able to deliver in some technology which can do a translation. Okay? And that is where you can see here, nanomaterials, nanoscience, etc. There are so many areas, especially in the energy sector, where nanotechnology is making inroads. So actually the application-oriented research of nanotechnology is now happening. Then there are dimensionality. Is a very interesting angle, and there are zero-dimensional, one-dimensional, two-dimensional, three-dimensional materials here. Okay, and that gives you another kind of handle on controlling the properties. And you will find here what the dimensionality does is that when you go from different dimensions, the whole electronic state spectra change. Okay, so when you go from 3D to 2D, whole electronic energy density dispersion relations are completely different. And now many people are working on mixed dimensional materials. So imagine a situation where on one side you have a 3D material and on the other side you have a 2D material. So it is not only the materials you are marrying, okay, but it is the electronic state difference which you are managing, and at the interface, very exciting phenomena can happen. In fact, when you talk to different people, there are many exciting phenomena people are discovering related to surface or interface of different materials. And that is where this new field is also coming, quantum materials. And you see, you talk these days about many body interactions, entanglement, topology, teleportation, quantum sensors, and so on. Many people believe, as I said earlier, all people were in nano mission making nanoparticles of everything they saw. Okay, and that was a basic quantum science effect. So many of them said that, oh, quantum technology is coming, I'm already there. Okay, it is not that. Making nanoparticles is not quantum technology. Okay, for quantum sensing. I make serious nanoparticle and I'm measuring sulfur sensitivity. That is not quantum technology. Okay, quantum technology is quantum accentuated phenomena which are very unique and which can bring something to the table which is very important. And now people are looking at quantum materials for energy applications as well. Okay, so quantum materials, you can engineer them in the emergent phenomena of various kinds, and people are discovering new forms of superconductivity, topological properties, and so on, which are very interesting. And in energy sector also that is happening. Okay, the other important thing is all devices that you see, energy devices, they are interfaces. So the most advanced science, which is in terms of energy science, is related to interface science. Okay, and these interfaces are molecule solid interface. In electrochemistry, you have metal liquid interface, and number of other things. So this is one of the hottest topics that there are now people who can say, I'm a mechanical engineer, I'm an electrical engineer, someone said I'm an interface engineer. Okay, it's possible to do that in another. The description of job description will eventually change. We want interface engineers, or let us say Tatas. Okay, so I will not be surprised if another 5 years those kinds of advertisements start coming for job descriptions. Okay, now this is where you have so many materials type, and I think material science is the least respected science. Okay, as compared to basic disciplines on the other hand, and some specialized engineering on the other hand. We don't give materials, as I always say, materials give wings to our ideas, our dreams. Okay, you make any idea, you make any plan. I want to send man on Mars, whatever. Who is going to do that? You know, you have to make a rocket, you have to make solar panels, you have to do sensors, you have to do everything. Everything is materials. Okay. So now when people actually see a mobile phone in their pocket and talk about that mobile phone and everything, they are very happy. Communications में कितना development हो गया? Common man says, बहुत development communication. Communication में क्या वो मोबाइल में 1 million people worldwide, 1 million people have worked on that, and every little thing technology has been put together to bring that communication. Fiber optics, all material science. There are fibers of hundreds and hundreds of miles laid in Atlantic Ocean. Nobody bothers about communication में बहुत development. Who did that? Material scientists like us have done that, and I think it is very important for us to very strongly and emphatically talk about it over time. Okay. Now, the other thing is when you talk about innovation, many students know what is an innovation and so on, and how we can do innovation. And it is very important that in this sector there has to be a pragmatic innovation. Okay, innovation in principle has to do something with eventual utilization. Okay, if you look at Wikipedia definition or any definition of innovation, innovation related to eventual practical utilization. Okay, even discovery, after discovery also a number of innovations happen before a product comes into play, right? So innovation has in definition some utility, but then we have to realize that it has to be pragmatic, affordability, and on the scale. So if we write a paper published in Anbuchem saying that I'm doing platinum-based catalysis, it is good for Anbuchem, but nobody is going to use that. So how to do a pragmatic innovation? Once you do a lot of platinum and you do that research, next question should be, instead of platinum, can I use some other material, some other elements, put them together in an interesting way to achieve at least 70% of that performance or even 50% of that material performance? So after I establish what is best possible for the catalyst by using whatever, freedom, no cost discussed. Okay, and suppose we come with that particular conclusion and we publish a high impact paper. After that, it will be good if we ask, can I use iron, silicon, copper, something, and make some particular compound of that, okay, and then establish a performance which is even 50 times that performance, but the cost will be 100 times less. In 10%, if you go to get 60% of that performance, that is pragmatic. Okay, so I think for younger people, it is important to realize that when we do publishable science, high impact science, it will be good on the side. If you think that can I translate this by doing this, even 60% of that performance, then that will be a very valuable thing, especially for any country which is going to put money into that kind of research. Okay, so it is very, very important to keep that on the back of our mind. And these are 90% of weight of Earth's element are these elements. So try to see if we can do something with these elements. Okay, rather than some elements which are maybe few milligrams in the whole Earth or something. Okay, so that is how we have to think about it. Okay, then the other thing before I go quickly over to something is circular economy and waste to value. It is also very important science, and I will tell you why the value. Look at this, 250,000 tons of unprocessed lithium-ion battery waste will be produced when electrical cars sold now will reach end of their life. So suppose you are all buying electric cars in another 8 to 10 years, if you are ready to buy a new car and the batteries give away, all that thing will be so much tons of all this waste will come, and unless you do something to recycle that and to reuse that, it's very difficult that we will be simply imagine also the complexity of the situation. Suppose we have all these cars on the road and by 2035 each one of us goes electric. Okay, and now we are buying all the batteries from China. We have no manufacturing even now in India of battery systems and so on. Okay, now if we don't have lithium, I'm going to show some solutions and some work that we have done. But if we have that scenario and if our relations with China soar and we don't get batteries, what are going to those cars on the roads? वो तो पेट्रोल डाल नहीं सकते, पेट्रोल नहीं है उसमें, okay, और बैटरी बंद पड़ गया. What are you going to do with all that? All these millions and millions of cars on the road will just be exhibits, okay, to show एक ज़माने में ऐसा कार हुआ करता. Okay, so that is why I think it is very difficult for us to understand unless we have peripheral technologies developing to the same extent, it will be hugely difficult to sustain the whole concept of sustainability. We will not be able to have sustainability, but even the concept will completely go unless we actually have some particular scenario, even virtual scenario worked out, how are we going to behave and how are we going to sort of do our innovations and sustainability. You see here, there are solar panels. Okay, I have also something on my home. Okay, and they say that by between these 30 years, there will be 7.5 million tons of this kind of waste. And all this is a pure silicon, highly purified silicon, doped, okay, and made into solar cell. See what is happening. Now, when we crush all this, there will be a lot of silicon. What are we going to do with it? Because it will have all sorts of elements like this. These are all elements go on into all these devices, computer waste, this waste and that. Okay, so this is something which we have no idea. In fact, to see what are we going to do with this silicon. If we crush this silicon and do purification will be such a huge thing, will it be able to convert itself? We will have its purity established to be able to do, solar cells again of some efficiency, or where is this silicon going to end? I was talking to some faculty member this afternoon doing deep level transient spectroscopy on all those kinds of things. इसमें तो इतना impurity है कि इतना ढूंढ क्या वो देखना पड़ेगा कि impurity free कुछ है क्या एक region, maybe 10 nanometers, 20 nanometers in which impurity is not there. It's very difficult once we crush this. So imagine the scenario. So I think what we will do is I will quickly go through some of the research that we have done to talk in the last 10-15 minutes about the industry angle which I'm supposed to say something today. Now these are energy devices and interfaces, battery, fuel cell, electrolyzer, all these kinds of things. And you basically need to make sense, you need advanced science, you need technology development, and third, lab to market. Okay, so you basically need a thing which relate to all these angles have to be incorporated, and therefore you need to do a lot of work here. Now, conceptually, when you teach these devices in the class, it all looks kind of simple. There is an anode, there is a cathode, there is a separator, you put some electrolyte, and the lithium goes here, comes here, back. This is all simple. But if you consider, by the way, the simple battery here, battery, in the battery, of course, you have an anode like graphite, you have some cathode which lithium is contained, and then you shuttle that back and forth. Lithium goes and sits inside the planes of graphene and then comes back, and in charging and discharging, you get your work done like quick charge or mobile, and you charge and discharge and charge and discharge, all those things happen. Okay, the picture is simple to understand. However, and now there are many new systems coming up. People are working on photo batteries. They are working on all different kinds of batteries. Now, sodium batteries is something which is taking space because lithium, as I said, has a problem. Okay, but sodium, there is so much of sodium in the sea. Okay, and sodium mines are also there, everything. So people are trying to see how to use sodium batteries. But sodium is a bigger ion. Okay, and therefore in the graphite, it doesn't actually, it can go inside, however, it doesn't form stable phases with carbon, bonding with carbon, and therefore it tends to come out. So it doesn't happen that graphite does not prove to be a good electrode for that. So people are using what is called as hard carbon, which is not graphite, but there are graphitic places here, and there are poodles here, which are kind of small regions, and also there are ways of trying to engineer the electrolyte to put sodium inside. So sodium has different material systems to be used there and to be handled. Okay, but sodium, if we do succeed, then it will be good for everybody because it is much more cheaper and availability is there and so on. Similarly, there are other types of battery systems which are coming up, and I will come to that later. People are saying lithium batteries are graphite here, and some kind of cathode like this. So people are saying that in this graphite, you are trying to store lithium, like here. Between the sheets of graphite, lithium is going. They said, what is the purpose of a battery? Suppose you have a battery, you want to shuttle lithium. So you use some energy, like we use charging for our mobile, you use electrical energy to push lithium from one end to the other. and store them. Now, when we actually use it in using our mobile, lithium goes back and sits back. Okay, so this is the reversibility. So what we want in the battery operation is you want to have lithium shuttling between anode and cathode. So some people say, why not do like this? Instead of this graphite, okay, can I have lithium metal itself? Okay, so there is a lot of lithium here. Somebody said, why even have a lithium metal, which is very thin, lithium metal, and then this lithium metal, you take lithium from here, take it there, you go back and lithium metal here. So instead of any lithium cobalt oxide or some compound like this, where lithium only occupies a small volume, let us put a thin slab of lithium. Okay, can we use lithium and shuttle back? But then it has hazards of lithium and so on. As well as there are some other problems related to that, which I don't want to discuss right now because they're a little bit more technical. But then some people say, why lithium at all? Let's go here and let's have a copper, which is a current collector itself as an anode. Okay, so now let us bring lithium from there and take lithium back, lithium from there. So you reduce the weight of the anode completely and your capacity, gravimetric capacity goes up and so on. These are called anode-free batteries and so on. So these are anode-free batteries. So no anode here. Okay, so there are many ideas like this which have been discussed, but they all have some problem. Okay? I mean, let me tell, by the way, there are so many batteries. Anybody of you are interested, the whole sky is open for innovative research, to be done in batteries, and there are so many different types of batteries. And it was in 2018, they said 10 disruptive battery technologies which are involving all these simple things are being considered here. Okay, so this is something which you need to take a look at and work on some of these. Okay, now this is the concept, basic battery concept like this, which I showed, but this is not something what happens in an actual battery. In an actual battery, the whole complexity is shown here, right? This is a classroom battery. Okay, when you teach, this is the battery. This is the practical battery. अंदर कुछ होता है, कुछ नहीं होता, कुछ बहुत कुछ होता है. There are so many phenomena which are going on that, for example, here this binder which you make this coating, people say, oh, graphite here. You have to stick that graphite on the electrode. There is a binder which is insulating. That binder also reacts with lithium. Electrolytes react with binder. Electrolyte reacts also with lithium, deposits something on the top. Okay. Then there is also, when lithium comes, lithium is also knotty. It can form, dendrites like this from the grains. It goes and the dendrite passes through the, membrane and shorts the battery on the other side. Okay. And then all these things, phenomena happen, and then you find all these fires and everything taking place. Right? We read in the newspaper that some scooter burned, some car burned, this kind of thing. All these phenomena relate to this complexity of phenomena inside. There is, through these reactions, some gas comes out. We have seen actually the batteries bulging like this, outside, and so on. So a variety of things can happen. So it is beyond textbook, and this is something which is the complex. You see all these things written here, and then writes everything, and we need to control and try. So the whole battery research is now trying to control how you can tame this phenomena. Okay, so over, let us say, 10,000 cycles that of the battery use, you will be able to handle it safely and so on. That is the research which is going on. Okay, so now the materials, so many materials, cathodes, anodes, electrolytes and so on. The science is very mature, and I will just go through electrolyte. This is all inorganic materials, many of them. Okay, but then there is organic chemistry of solid electrolytes, organic chemistry of liquid electrolytes. Okay, so you see here chemistry, physics, material science, chemistry, everything is coming together here. Organic chemistry is sitting in between. Soft material science is in between. That is the separator, which is like separator has to have properties which is mechanically strong, porous to be able to conduct ions, but electrons should not go, and so on. Electrolyte has to be such that it doesn't produce too much reactions, too much side reactions, too much gas, all that. This side is your current collector, which should adhere the electrode properly. The other side is another current, reaction should be limited, and so on. Too many complications. So it is not something which is simple science. And then you have all these reactions and scenarios and so on. If anybody is interested, I would be more than happy to share some of this presentation. A PDF copy, please write to me, because these things is very difficult to take the time to discuss this. So I will just give you a few examples of some of the research that we did. For example, see, when I was talking about here, the battery. Okay, so here, many times what happens is this is shown as a big grain, but when you have a powder deposited on, say, anode, lithium is coming in and going out, coming in and going out, and coming in meaning inside bulk of that graphite it is coming out. Or any other anode that I do, it is coming inside, reacting, forming an alloy, forming a compound, or intercalating, whatever happens. You can imagine a situation, where you have a nice coating to begin with. But as you have a lot of lithium coming in and out, there is a possibility that the whole bulging takes place. Okay, you can imagine the entire lithium going inside and coming out. It leaves some pore, the morphology changes, and so on, and finally some specks can come out. Okay, and now many people had something that this material. Okay, this is paper of Dr. Kimshuk Roy, who is present here. Kimshuk, can you stand up? Yeah, he has just returned from Purdue University and joined our institute. And the only difference I see is that Dadi throw a hair. Okay, Kimshuk, that was just a joke, side joke. But he has published some very nice work from Purdue and from us. And this was one of his papers earlier, where this phenomenon of volume expansion contraction is called pulverization, and the whole electrode falls apart. Okay, it breaks electrode and the battery goes back. Okay, silicon is a material which can bond with 4 lithiums. So there are compounds silicon can form, like Si4 lithium 15 and so on. So people say, oh, that is wonderful. It is not. You can actually have a high capacity silicon. So if you make an electrode, you will have a really high capacity silicon anode material, because you have a lot of lithium can go in. But a lot of lithium means it can literally breathe like this. The electrode will go like that, and finally the electrode will fall apart. So what we thought, and many people had tried something else, right? You can put some elastic material, 2% inside, like graphene or something else, so that it can still hold on while this breathing is going on. By lithium coming in and leaving out, it can still hold that electrode. Can it hold? Okay. So what we did was we actually used here phosphorine. Here. Okay, it is about 8% phosphorine. Okay? Now phosphorine is a very interesting molecule mechanically. I always call it like an accordion. Okay, accordion. Okay, so it has this staggered arrangement. Okay, so it can be pulled like that. Graphene cannot be pulled like that. You take graphene like a sheet of paper, bond paper, try to pull it, you cannot pull it. The same thing is, you have to tear the paper, right? You cannot pull. There is a lateral plane elasticity is not there. Similarly, graphene cannot be pulled. Graphene can be flexed, okay? But graphene cannot be pulled. But this accordion can be pulled also. So you have more elastic degrees of freedom. So we thought this will do good. And you see what a difference it makes. This is a term that we got. The battery completely collapsed because of this polarization problem if you don't use phosphorine. Okay, and this is a curve similar to 1,000 people who have bought worldwide. Okay, this is no different. Our result is the same. In about 30-50 cycles, the whole electrode falls apart. But then when we put 8% of phosphorine inside, see what happens. Up to 250 cycles, the capacity here is around 1500 milliampere hour of that, which is silicon capacity. Initial capacity is very high, like 3000. But at least we could maintain half of it. Okay, it didn't fall apart to zero by doing that. Yes.
If lithium really forms bond
Yes.
with silicon,
Yes.
then how do I delithiate the whole?
No, that thing, whole thing happens like a reversible cycle, electrically driven. So it's
So
debonds.
it really
Yeah, debonds. Alloying. This is called alloying, and it debonds. Okay. So you see this huge difference from zero. We have been able to sustain up to 1500. So this is one way. I was just giving an example. Then there were other things we have done with Professor Vaidyanathan, who is not there, and Kimshuk is also here. Then Satvik's PhD program, this was their equal contribution. And this Profs and other types of material have also some porosity, as well as you can engineer the molecules inside. These COFs are something where you can, and here Pradeep himself is doing very good work. He has published with Abhi recently an IUCAM, which was important. So these COFs are very interesting materials in which you can molecularly engineer the whole structure, and therefore with what lithium will bond, and they also have spaces here through which lithium can diffuse. So these are kind of porous materials which are chemically active, redox active materials, and therefore very interesting. I'll just show you, we have done some work here, and these are some high impact paper. Thanks to Vaidyanathan, we actually did battery work, but he was the one who designed all these different molecules, which are very interesting, and actually did deliver that particular thing. I just want to say inside that we have done some work even in soft materials for batteries. And you see, I have my respect for chemistry has grown like anything, because these people, my students, can actually synthesize anything. We just tell them that ये कर सकते हो क्या? So they say, oh yes sir, वो करके कुछ molecule डालेंगे, they will prepare something. Now this Yogesh Gowdy, who is now in UK, senior manager in a company, Leon Volt, in battery, he did this work. Actually, we were trying to see if polyaniline architecture can be used for battery supercapacitor performance and so on. And it turned out that when we do this polyaniline architecture, actually when we do 3D polyaniline, it forms like a blob, like this. And we said a blob, it doesn't have enough porosity for link to go inside. Then he said that if we do weak acid instead of a strong acid, it may form a different morphology. So he went and did something, and it became a porous morphology. But that weak acid did not lead to high electrical conductivity, because polyaniline conductivity comes with the fluorine groups and so on. Okay, so weak acid led to a morphology which was open structure, but this leads to like a blob-like structure. Can we mix this? I didn't know. I'm not a chemist. So I said, can we have porosity, maybe a little less, but conductivity maybe a little high? And he did that. And he actually did a dual acid. So instead of phytic acid doping alone and HCl or doping alone, he mixed, we can in succession and produce an intermediate morphology, which had a good conductivity and reasonable porosity. And then we found that even at a capacity of 40 amperes hour per gram, up to 500 cycle, this polymer was a stable electrode. Normally, polymer is a very fragile kind of thing, and under lithium attack, going in and out, you expect it will fall apart. But it was very important that up to about 500 cycles, it kind of was quite stable if you do engineering properly. Okay, I will also tell something which we have done partly but not published yet, and I wanted to show this slide to Anushri. Anushri is my granddaughter's name, by the way. Anushri. Okay. So I wanted to show, because what we were doing is we were doing some work just about 10 minutes. Okay? We were doing some work on this Fe3SnC anti-perovskite material, and when we did that, we found that we were doing DFT calculations, and for some reason Mujaffar here tried to do the spin polarized calculations, and it found that the material has a magnetic, and it actually changes magnetism here, and it has conductivity also. The Fermi energy here, you have density of states at Fermi energy, so it is conducting material and it's spin polarized. Okay, so we asked what happens with lithium battery. Okay, so when lithium goes inside and out in this material, we found that the magnetism is changing like this, and this curve as the experimental curves are these three. Okay, and these two are spin polarization computed. Okay, and you see that it is kind of spin is also changing. The magnetism origin, see magnetism, there are many insulating magnets, so that is not spin polarized. There are many metallic magnets with zero spin polarization, but spin polarization is the differential spin up, spin down density of states at the Fermi level. So you can then have conducting with majority spins over minority spins, that is spin polarization. Okay, so I was saying that this is a new thing which is coming up now. Can you actually, in the battery mode, I can make a spin polarization battery. That means I can have lithium going in, spin polarization goes up. lithium comes out, spin polarization goes down. So you can actually have there has been a floating concept of spin battery, but there is nothing on spin polarization battery. Okay, so I call this ionospintronics. Okay, so because I've given that name and we have put it on something, there is no such word in the literature so far. So ionospintronics, can you do ionospintronics? Okay, so this is something which is very interesting with batteries. You can play some games like this which are interesting. Now I will just breeze through a couple of slides and go to my main thing, industry related. So carbons. Carbon is such a beautiful material and it has many applications in batteries and so on. And I will just indicate a few. This kind of porous carbons we can make in various ways for supercapacitors. We can make carbons. This was our paper, where we make also supercapacitors from dead leaves. And this was at that time in 2013. This tree was outside my office in NCR. Okay, and every day we were walking for a cup of tea. My whole group used to go for a cup of tea, and that guy was taking those leaves and burning them. I told my student Mandakini, why don't you collect some and let's see what are the things there and we can do something about it. So we actually carbonized that with pyrolysis in a controlled way and found some very valuable porous carbon here. Okay, like this. And it showed an absolutely fantastic supercapacitor property. And we got energy environment to science paper on that particular simple idea and trying to pyrolyze making carbon from that. And I will tell you just a joke that one Canadian professor wrote to me. Okay, he said after reading your paper, I wrote a proposal to their NSF in Canada, and he got a huge grant because Canada's symbol is leaf. And he said our leaves are all, see, our problem is every tree has a different leaf. So we don't know how to collect that and get a reproducible carbon for industry. Okay, he said we have no problem. All our leaves are similar type, and he made a lot of carbon using that after this. So this is just a fun thing, and I was just happy to see that somebody got some money out of this research, although we didn't get them. So okay, so anyway, I will not go into these details. We have also done some work on carbon, trying to do laser treatments here using carbon. And let me just go to my task of industry. This is dendrites formation and so on. See, actually I have so many things to say, so I can never stop. So I will just rush through some of the things here. And we have been able to understand how dendrite formation takes place and how to control them. Because dendrite is, as I said, dendrite rushes through the separator and shorts it completely and the battery goes off. So you have to suppress. So what we have done is, I will show only this one. Okay, here Neenal Wabe, who is now in Maryland, student, what we did here was we did laser treatment. We took furfural alcohol, which is kind of some organic agro residue, and we made a coating on that, and we use CO2 laser. This CO2 laser comes in 3 lakh rupees, okay, and made in India also, 3 to 5 lakhs. It's very cheap, but we can do a lot of fun with it of direct writing. So we did that, and we did this direct writing and produced a gradient pattern of carbon here, okay. And then what happened was we found that this was the dendrite growing without that layer, and this happened after we grow. See the difference? Flat lithium grow, while these are dendrites here. When this was not done, only copper was used. Then we get full dendrite formation here. While when we actually did that laser treatment and a thin layer of carbon on the top of copper, we found that you see this flat lithium growing completely like this, and all the other things we did with it. So dendrites have to be stopped, and you need to surface engineer something, and we used a laser beam to be able to do that. Okay, so other things you can do, manage electrolytes and so on. Let me not go there. Let me come to something important. I will just rush through certain slides here, and lot of stuff, but my talk is very general. All this something on perovskites and so on, some of our articles, but let me not show you. I will come to this in the last 5-7 minutes and just talk about this. Okay. Now, we are talking about industry, academia, government nexus, how everything happens here, and what is happening in our country. And if you see, all of them have national interest, national interest, national interest. So it is one common interest that all three of us have. Now, if you take government, it has also international interest because how our country is to be placed in the scenario of international interest is important. Academia have academic interest, career interest, but they also have national interest. Okay, career interest is winning awards, getting high impact papers, getting recognitions. That is our interest. Okay? Now, industry has economic interest and growth interest. They want money. They cannot do anything just by supporting something, and they have growth interest because sustainability is not in industry interest. Any industry which says that it is sustainable is dying. They have to keep a upward path. Okay, ऐसा हो गया तो नीचे ही जाता है. You know, this has happened. So they have a growth interest also, but they also have national interest. So what we need to do is how government, what they are going to supply there, okay, what the subsidy, supply chain issues, infra, how they are going to solve, industry, academia, mutual confidence and respect, mutual value of interaction, they have to realize. Many people will say, why don't get anything from? No award by interacting with an industry. Okay, why should I do that? No reward of some kind. Okay, so value system is there. So what also the problem is, everybody understands this problem, but these three wheels have to be working together. What is happening with us is that we know what is wrong, and these are all experts. We have very good industries who have a lot of money. We have very good scientists who can do a lot of good work. We may have a good government once in a while or for another 5-10 years or something, whatever. Okay, but then all are not working synergistically. So if you imagine there are all the best players, okay, maybe Zakir Hussain, maybe somebody else, all of them, but we are asking them to do whatever they want, it will be noise. Okay, unless they all work together, there cannot be a music. So there is a difference between music and noise. Okay, so what is happening is we have everything that is going on good, but together synergistically the harmony is lost and we don't know how to put together. I will now give few examples of some work that we have done. We have done with KPIT company in Pune, sodium ion battery technology. This is maybe 10,000 crore company. And I would like to tell you, I was telling you, industry always is happy to give you in-kind support. Okay, they say, our project hai, hum in-kind support denge. And we are very happy about what Mr. Pradeep Pascu is doing, and will give in-kind support. Okay, in-kind se kuch hota nahi. You know, so many industries came, we told them that doesn't have a value. Now this company gave us in a period of 6 years 2 crores of rupees cash actually to do research work. We employed people, we use consumables and so on. And just about 7-8 months back, the technology announcement was made and their technology is being evaluated for possible manufacturing, okay, by a US company. So they are doing due diligence now. This is a real money spent over about 5 to 6 years to do research. This Livguard company, they said we don't want sodium, we want LFP lithium for 3-wheelers, all these Totos and 3-wheelers and rickshaws like that. So we worked with them. They gave us in 4 years 2 crores of rupees, okay, and developed that technology. There is a company from UK, Kilkington, which is Nippon Sheet Glass company. They are doing this silicon high capacity anode, which is what I gave Kim Shuk's work example. Let's say put phosphorus, put something, try to push that capacity. So this is what we have done, and all these particular levels, KRL levels, buses, etc. This is all technology is being transferred. This is the CEO. He is recently added into the Forbes list of billionaires from India. Okay, he is recently in the top 100 from India, and his vision actually led to this particular development, and he gave actual money, not BST money, and then we are supporting in kind later. This is a real money, and the entire work is done, so we are not conflicting with anything. Okay, he's another visionary, Rakesh Malhotra. You can see he has companies called Livguard. Your inverters in your homes may be from him. Okay, because he has some 30% market of inverters here. Okay, and they also have Live Pure. They do air purifiers, water purifiers, and Akshay Kumar and Sachin Tendulkar are their brand ambassadors. So when he came to talk to me at ICER, and we had a discussion at least 3 times, I told him, you can give me money, funding for this research we'll do, happy to do, but can we meet Akshay Kumar and Sachin Tendulkar? He said, always. You know, I saw on your website, That's the fun. But we did work with him, and we also produced battery. And now recently they have done 25 ampere hour battery. Now this has gone to 5,000 cycles. And the most important thing is, both these companies have about 6 to 7 people who worked on that project are all hired from my group. Okay, so this is something which is very important. This is also with Pilkington. This is waste glass converted into silicon. If you know, nano silicon looks brown, by the way, if you have done it. Okay, and this is a high capacity of silicon we have done for them. We are still working on a new project with them. Okay, and this is about our institute. In another 2 minutes, I will tell Dr. Purnendu Chatterjee, who is actually alumni of IIT Kharagpur, BTech Mechanical Engineering. Then he went to Berkeley and did PhD in operations research. Okay, and then went into McKinsey and McKinsey investment. Then George Soros and company made billions for them, billions for himself. Okay, he's also a billionaire. Okay, but he has 13 companies of his own. Okay, including Hollia Petrochemicals. Those are the kind of companies. And he decided in 2012 or 2013 to launch an education institute for R&D. Okay, and he decided he has put through their corporate social responsibility grant, he has put 500 crores to establish this lab, TCG CREST. Okay, out of which 100 crores are for the lab which is called the Research Institute for Sustainable Energy, where I am a director now since 2020. Okay, and there are 5 other verticals, like you can see here. This is IAI, Institute for Advancing Intelligence, AIML. Then there is Quantum Technologies. Then there is also Chinta, which is Advanced Neuroscience, autism, Alzheimer's, okay, all those kinds of diseases, research and so on. So this is the institute now, which is generated and all. This is 15 minutes from here. You are all welcome. Just write to any one of us and please visit us. And you will just love to see that. And I think Tanushree, you have been there very early. Now it is time because a lot of things has been established. So I invite you properly there to again see with your team. Okay, and these are our labs there for RICE, which is the laboratory which I am heading, and we have about 50 plus people and all that. These are our labs, which is first-rate facilities established here, and we have high-end equipments here almost and generated. Okay, and I was telling you about industry. These are people in the last 10 years from my group who have got jobs in industry. Okay, there are many in academia, but I'm showing some younger people that the market of battery green hydrogen research is so high that you can see she is in MIT startup. She was earlier in Princeton as a postdoc after doing PhD with me. She went to Purdue first, in Princeton, and now landed in MIT startup, Dhanya Puthuseri. Rohan Gokhale is head of the cathode division of Umicore, which is a humongous company. Okay, he's the cathode division sales engineer. He's in Leon Wood. These are KPIT, Ola Electric, Mahindra, Leogard, okay, Dyson in UK, Ola again, a number of other people there, KPIT and so on. So you can see in 10 years, in about, not even 10 years, about 9 years, there are something like 21 people who have got, and I will tell you, Neha Sharma, she got immediately after PhD a package of 24 lakhs per year in Ola Electric. So that is how 24 lakhs package, fresh PhD. Okay, but some other fresh PhD got 20 lakhs, but not much less. Okay, so this is now when academia, industries, many people are not getting lecturership even or assistant professor position. At ICER, we have 92 applications for one position, and many of them from Oxford, Cambridge, and all that. It's very hard to get anybody there. So there are these opportunities which are coming if you do some applied research as well in addition to fundamental research. So I thought I will tell that message. And these are some battery science. All of them are doing battery science. She's in Germany and a number of other people elsewhere. Okay, and this is our institute, and this is all 90% of people here are from our institute. There were about 85% people, and about 15-20 people from outside in this in-house conference that we had held when Shirley Meng, who is one of the top battery persons, she had visited. We held an in-house conference. Abhig Banerjee is here, who is our principal battery scientist, with whom he has collaborated recently, and there are a number of other people. So this is not a very small operation anymore, and this is only one vertical. There are 5 verticals like this, so it is more. Okay, and we want to do something very good here, and you are most welcome to come and collaborate. First, come and see what we have, and you will see. And most welcome. Thank you very much. I will be happy to have a few questions or whatever. Yes.
Wonderful talk.
Any questions, comments? Please feel free to ask.
Yeah,
Yeah.
these are all very interesting, very fascinating. But how do you get this idea? For example, with the laser, the kind of patterning you did. So, how
I
that
will
idea
tell you,
triggered?
for me, I was working with CO2 lasers and excimer lasers for a long time, since 80s. Okay, so when the idea came that there is a problem of lithium wetting, okay, on the surface and so on, you obviously have to engineer. Now, some people coat something and do something, but the coating externally, then you heat it, and the bonding, and then you have to have binder. So I wanted to do something binder free. Okay, so you coat something which is carbonizable, and then you can have localized heat. Because if you put into oven, you are really wasting for 10 centimeters where the whole oven is heating up. So this is energy saving also. So you are delivering energy where it is needed. So it is like a direct writing. So I thought let's do this, and then you just sonicate a little bit extra material, and you get an extremely thin carbon coating. And we had done another work in which we found that carbon can have a weighting of lithium better. Then the other question is, if you have that material and if lithium comes and it laterally diffuses faster than a 3D diffusion like this, surface diffusion, then it will not form dendrite, but it will form platinum. So it was some kind of experience, with this, playing with these things.
Another thing, of course, I'm not exactly from this field.
Yeah.
There are also, as you showed, I think in one of your slides, that people have tried to put some kind of quantum dots attached to the anode or cathode,
Yes.
and by that way they wanted to, kind of enhance the
Yeah.
performance.
So basically what you do is some people infiltrate quantum dots, generally carbon dots
Yeah.
or graphene dots and
Yeah.
so on inside.
Yeah.
So they have certain property of adhering on the grains and modifying the surface reactions to some extent. Okay, but generally nanoparticles are not good for battery electrodes because they have large surface area. Okay. Now when electrolyte is there and lithium is also coming and solvent is there, because the electrolyte is like a solvent with some salt. Now they react with lithium, and more the surface area you can
They
pour
will
more of that. And when it becomes too thick, then resistance is built up and your performance goes down. So generally people use powder where the particle size could be 10 to even 50 micron size. And then you pour that. So you don't want too much surface area unless it brings specific benefit. So now what happens is people have done quantum dots as additives in electrolyte, which will compete with the adsorption and control the reactions on the surface. There are some interesting ideas to do.
Okay. Thanks.
Yeah.
So I understand 1 dimension, 2 dimension, 3 dimension, like integer dimension.
Yeah.
But how do I visualize 0 dimension and fractional dimension?
Yeah, fractional dimension is something different. Okay, like a fractal structure. Fractional dimension is something where if you look at fractal structure growth, that is fractional dimension. But if you consider 0 dimension, it is quasi-zero. Even 2 dimension, if you have a single graphene sheet, that is real 2D. Okay, but generally when people exfoliate, you can get 2 or 3. So we call it, for example, few layer black phosphorus or few layer graphene. Okay, and you can actually count the number of layers you have from Raman spectroscopy. Okay, so I can know whether I have one real 2 dimensions or quasi 2 dimensions. Now, ideal 0 dimension means that all 3 dimensions are quenched into a small volume. That is a practical definition. There is nothing 0 dimension. It is a quasi 0 dimension.
Yeah.
This is some loose talk in science. 0 dimension.
Hi, fascinating talk. I have a philosophical question.
Yes.
Like we have been taught to love basic science, and we have been practicing it for a long time. I think you also did it in some part of your career. Now you want to switch to sort of technology. There is a mental barrier. Okay, I mean, at least for me, there is a mental barrier.
So let me tell
How to
you,
cross it?
let me tell you one thing that, when I came back from US in 2006, before that, I was totally spintronics, superconductors.
Yes, I know. Yeah.
Yeah, but I was going to come to HCL and I said I will be in the sea of solutions around me. And can I find some solution for myself, okay, to be relevant in NCL, okay? And I said that if I talk about spintronics, it will not make any sense there in National Chemical Laboratory. But then I can leverage the strength of chemistry, which is around me, okay? And I always thought that I wanted to work at least towards the latter end of my career on something where I will see the fruits of my research, okay, while I'm alive. Okay, so that was my psychological thinking. Okay, if I continue to write papers, etc., one day I will die, and I will never know, any of my research will ever be useful at all. So this was my selfish intent that toward the end of my career, I'm 71, just 24 July I became 71. Okay, so I said, वही paper और एक करके क्या करेंगे? वो तो हो गया. Abhi, at least can I think of a few parts? I'm not doing entire applied research. I still published in physical applied and all those kinds of things, but physical applied, physical material, rarely physical B or PRL, which I did earlier. Okay, so abhi kya hai? Abhi I think of whatever research I'm doing, whether I can take one step and somebody can find a use of it. Okay, basic research is extremely important, and people who are very good at it continue to do it. So this is a choice that you make. Okay. For example, say देखो, Raman effect. When Raman discovered it, it was purely important for quantum mechanics, where people at that time he got Nobel Prize because the quantum mechanics development was going on, and people always thought that photon, how कुछ नहीं होगा उसको, and that exchange energy with material and you actually deliver, gave and so on. So it was fundamental issue that he sorted out and observed based on that. But we never knew that Raman spectroscopy will be there in every lab, sorting out every solutions and helping people in that way. It was not given because it was useful for material science. The Nobel Prize was for an entirely different discovery of sorts. Okay, so it is important. And some of those discoveries will have value after 70 years. Okay, that's fine. I think some people are very good at it and they will deliver and so on. But for me, I thought that there are certain current needs of society. If I do some part of my research, okay, which can have relevant, so otherwise I will say industry, I don't want to do industries. Why not? I can spend 20% of my time, 30% of my time. Rest of we are still producing Anguchem and all the JMC and all papers, high impact papers, advanced energy materials and on. We are doing the same thing. In our laboratory group meeting, we don't discuss industry research. We discuss only basic scientific research. But if industry approaches you, okay, that suppose you develop some characterization method and some industry says this is important for us, can you help us a little bit? Why not say no? You can welcome it. That is the only change. I'm not saying that you should stop basic science to do applied science. Not like that. But if there is an offshoot where there is a possibility of helping somebody, okay, why not do that? Don't completely transform yourself, because that our liking is not completely going into industry. Yes.
So you said the industry comes and asks for help.
Yes.
Then the scenario, or you also reach out?
No, through these kinds of talks, when we give in broad conferences, some industry, for example, I was invited to give a talk on sustainability and energy in a conference on powder metallurgy. Okay, and something. I don't know why they called me. Somebody must have told them that I can speak some nonsense for 1 hour. So basically, they called and then I gave a talk. After that, at least 7 industries approached.
So that
Like this.
the conference, which was also
Conferences are very important,
in which
some
industry
general
were-
broad talks can help.
So of course, I was trying to highlight one thing. So experiments and theory. So I guess whatever you are seeing translates well if you are doing experiments. industry reaches out, or you go to a conference where there is a larger chance of having industry partners, etc. What about theorists?
Theory now, with data science, AI, industry is going to come with theories.
So, but
A
suppose
lot.
someone
Materials discovery by AI. It's a big thing for
No,
industry.
but that is also okay. For a theory, it's also a niche area. Materials discovery using AI, that's a niche area. Suppose you are not working there, then how will you
So for example, give an example of a theory.
High energy physics.
high energy, quantum
High
field
energy
theory?
physics, the industry is not there.
Or the people who are doing quantum field theory or things of that sort, which
Yeah.
involves a bit
I
of
think every theory may not have industry
May not.
opportunity. Because there will be some exotic areas where they are doing. So we can't expect that industry will have something.
So for such people, we have to change ourselves to match up with the industry.
No, you don't have to change. You do whatever you are doing best. I think. I'm not saying
No,
everybody has to do that.
No, that's understood. Suppose they also would like to contribute to society.
Yeah.
Immediate
So for
then they have
example,
to
see,
tailor their.
I know the way you are thinking is something which reflects on the quality of our young people. They want to do something for society already. Even sustainability, wherever I go, students come and ask me, "Hum kya kar sakte?" Young people are more responsible than our generation about sustainability, cleanliness, purity. Young people want to do something. Okay, so abhi dekho, you can always engage with certain NGOs who are teaching students good science. Okay, that way you can help them grow into their careers and make good citizens, good students who will do something
No, but that
eventually.
is for industry collaboration.
Industry
Something,
collaboration.
some other group, which is also.
There are different ways.
I was talking about contributing to society through
And even I will
industry.
tell you, if you are even in those fields, if you have model making of certain model and you have certain capabilities, nuclear reactor model, you are doing something related to phenomena there. If there can be a code mapping onto, let us say, chemical industry, okay, of whatever you are designing. It will be very important. If you are designing some theoretically a material which is extremely robust and high temperature stable composite, you can certainly announce that. I would say you should announce a newspaper. Okay, some industries will come and we want to know about it because although you have developed it for nuclear reactor, radiation hard material, people will be interested. Because we don't see researchers were generally shy. We don't advertise ourselves. Okay, we will publish papers and we are happy. We go for a party, drink a bit, and then everybody is happy. Okay, after that we are not going out. Many people are not doing general talks in general fora. Okay, so therefore industry don't even know. So there have to be more industry academia interactions, and they will find making inroads into that area.
We conclude over here.
Thank
you, Professor.
Thank you. Thank you.
She is actually heading the